Assalamu alaikum. My name is Moaaz Ahmad, and in this video I am going to do a presentation for our DLD project, which was design a line follower robot using digital logics. So what is line follower robot? A line follower robot is such a robot which follows either a black line or a white line. So in this robot, we uses IR sensors to detect the black line along which we want it to move. So we were required to use at least 4 IR sensors in this robot, and we could either use the gate implementation or we could implement the robot using muxes. We decided to go for the gate implementation for our project, and for this, first of all, we took 4 IR sensors and 2 motors, one for left tire and one for right tire, into consideration and made a truth table for which is this one right here. And you can see here that we have a whole set of 16 readings for left sensor and 16 for right sensor, and 32 for both center sensors, which were to be placed in the center. They were required to focus on the black line so that our robot can detect the line and move accordingly. And we have the left motor right here and the right motor right here. So from this truth table we can see that if all of the sensors are 0, then both motors will stay put, so which means that they will not move at all. And if all of these sensors are on, which usually stands for a T position, a T point in which it shows black lines in all sorts of directions, means in the forward direction, in the left and in the right. So in this case our both motors will also be off, because in the robot will not understand in which direction it wants to move, as it is getting inputs from all sorts of different directions. So we can see here that if both the both the center sensors and the right sensor are on, which means that it wants to move in the right direction. So left motor will be on, which will cause the robot to move in the right direction. And same is the case with the scenario if the left sensor is on and all the other sensors are off, then it means that there is a black line on the left side, so the right motor will turn on, causing the robot to move toward the left. So these are the all of the scenarios, and this one right here, the last one, in which all the cases are all the sensors are on, this is usually called a user test case, so that we can know that it works correctly, all of the inputs are work correctly. So let's move on to the next. Since we decided to use gate implementation for our circuit, so we took all of the readings from the left motor and placed them in the K map so that we could get our equations for both left motor and right motor. And right motor will be the next one we will be discussing. And so I placed all of the readings from the left motor table into the K maps right here and derived these equations. So how could I drive these equations? So I have placed all of the inputs here, and we can see here that I see a set of 4 ones right here, and we can see here that the name here is A bar B, which is this one, and another set I can see here is of these 4. So I will place them right here as A bar C, since both of these have A bar in common and both of these also have the C in common. So I will say A bar and C. And the last one is this one right here of these 4. So we can see that these 4 also have the A bar in common, and the other thing they have in common is D. So we can place A bar D here. So the three of them combined will form our equations for the left motor, and using these equations I could drive the circuit diagram, and we can see here that since these two are multiplying with each other, so that means that they are using our AND gate, and so we place both of them as input in the AND gate, and this one is an AND gate 2 and this one is an AND gate 2. So we have three AND gates right here, and all three of these products are adding with each other. So we can assume that these three are in as using as these three's output are being used as an input to OR gate. So we placed their outputs as inputs in the OR gate right here. So now coming to the right motor, same is the scenario with the right motor. We can see here that we have placed all of the inputs in the from the truth table in the K maps and derived these equations in the exact same way like we did before. And using these equations we had derived our circuit diagram, and we can see here that these equations are also using 3 AND gates and 1 OR gate. So this is the equation for right motor, and this is the circuit diagram. So let's move on to the next slide. Now we wanted to implement the circuit in Proteus software so that we could get its PCB layout and moreover check if it is working correctly or not. So we implemented the circuit in the Proteus, and we have 4 inputs here. For inputs we used logic toggles, and to inverse the input from the left and right sensors we use a NOT gate for each of them, and then we are using the AND gates, total of 6 AND gates and 2 OR gates. As we recall from the previous two pictures, we can assume that each of them had 3 AND gates and 1 OR gate. So these are here, and both of these OR gates are giving output to left and right motors respectively, and causing them to rotate in the desired direction. So this is our gate level implementation, but during the implementation of this approach we realized that this approach will cost us more as compared to the MUX implementation. So this implementation could also result in a major error while working with the hardware, as if there is something wrong with the hardware we had to check all of the ICs one by one to detect if there is one fault, if there is any fault in any of them, or if the connections are just wrong. But with a MUX based implementation we are keeping ourselves away from these types of headaches so that we can avoid them by simply checking maximum of 2 ICs and moving on to our solution. So now we will check our MUX based approach. So for the MUXes we use rudimentary logics to drive the equations for the left motor and right motor. So what we did here is that we took the readings, we took the set of 2 readings from each of the left motor and then the right motor and compared them with the readings of right sensor here. So we make sets of two readings from this total of 16 readings, and so it makes a total of 8 sets. So we can see here that in the left motor we have 0 1, which is exactly the same as the right sensor, so we place it equal to right. And the next one is, it says here 1 1 and here it says 0 1. So since it is 1 1 right here, so we assume it to be 1. permanent one. And the same is the case with the next two, as both of these have 1 in their parts, and the remaining four have 0 all the way. So we will take all of them to be equal to 0. And from these sets we make the equation for our 8 cross 1 mux, and we can see here that since the first set is equal to r, so we take it equal to r plus, and the next three are 1, so we say plus 1 plus 1 plus 1, and the remaining 4 are 0, so they goes here. And same is the case with the right motor. We take its readings and compare it with the right, as first two are 0, so we say it is equal to 0, and the next one is 1 0, which is exactly opposite to the right sensor here, this one 0 1, which is, so we say it is the inverse of right, so we say r bar or r complement. And same goes for the all of the rest readings, as you can see here. So our right motor's equation is something like 0 plus r bar plus r bar plus r bar plus r bar plus all the way till the end. So this is our rudimentary logic, and we will use these equations and these readings for our mux implementation using 8 cross 1 muxes, 8 cross 1 muxes. So this is our diagram for our mux implementation. This is kind of a block diagram, not it is implemented in the Proteus software. So if I open the Proteus, so this one is a more clear version of our diagram, and we can see here that there are two muxes 8 cross 1 that we are using, though the serial number of these two muxes is 74151, and each of these muxes have total of 8 inputs and 1 output. So this mux right here has the, so this mux right here has the left motor connected to it, and this one has the right motor right here, and both of these motors are then connected to the ground. Now we can see here that since the left motor has a total of 4 zeros and 3 ones and 1 right connected to it, so we can see here that the first one of its input is connected to right here through this path, and the next 3 are connected to 1, and the remaining 4 are connected to ground. So same is the case with the right motor here, as we can see here that most of its inputs were the inverse, of right, so we will make a set of them and connect them to a NOT gate which has the input from the right sensor. So this is our mux level implementation, and then we connect the remaining sensors to our ABC and ABC of 2 muxes. So this is our mux level implementation, and now we will take this implementation and make it in the Proteus. So this is our truth table again, and these are the two equations. So this is our mux based implementation in the Proteus software, and you can see here that we are using the four IR sensors which were required by our instructor to, as we were required to use at least 4 of them, and we are using two 8 cross 1 muxes, and one of them is connected to left motor and one of them is connected to right motor. And so this is our basic mux level implementation in our Proteus software. Now after we have checked its simulation and checked if it's working correctly or not and removed any errors, now we can move on to our breadboard implementation. So for this we bought these components from the market, and we also bought some extras of them so that if something goes wrong or some component gets burnt, so we have a spare. So moving on to next slide, this is our breadboard level implementation. So you can see here that we have placed all of the sensors right here, and we have implemented a lot of wires here and connected the ICs with each other, and then the ICs with these motors through the motor driver. The motor driver is basically used for keeping the motors in track, so that they don't get too much load or too less load, so making the load constant that is being passed to them so that they could work without any fault or without getting burnt or without giving us any problems. So this is our mux level implementation being implemented on the breadboard. So this is a more clear look of the same circuit, and we can see here that these are all our 4 sensors, and this one right here is a motor driver. Oh, sorry, this one is the extra motor driver. The real motor driver is somewhere right here. So this is a video, and
ये हमारा लाइन फॉलोइंग रोबोट है और इसके अंदर हमने 4 आईआर सेंसर्स यूज़ किए हैं, 2 मक्सेस यूज़ किए हैं जो कि 8x1 है और 8 नॉट गेट यूज़ किए हैं। ये हमारा मोटर ड्राइवर है और ये रोबोट चेसिस और ये 2 व्हील्स हैं। और अगर यहाँ पे हमने 5 वोल्ट की इनपुट दी है और साथ ग्राउंड किया हुआ है, और यहाँ पे अगर चारों सेंसर्स की वैल्यू जो है वो 0 है तो रोबोट के दोनों व्हील्स स्टिल पे। और अगर मैं सिर्फ राइट सेंसर को ऑन कर देता हूँ यहाँ से, और इस वक्त अगर आप देख सकते हैं कि लेफ़्ट मोटर ऑन है और लेफ़्ट व्हील रोटेट कर रहा है, यानी कि ये लेफ़्ट से राइट की तरफ टर्न करेगा। और अगर मैं राइट को फिर ऑफ कर देता हूँ और इस बार लेफ़्ट को ऑन कर देता हूँ, अब आप देख सकते हैं कि सिर्फ लेफ़्ट वाला ऑन है और बाकी C1 C2 और राइट ये सारे ऑफ हैं। तो आप देख सकते हैं कि राइट मोटर टर्न कर रही है जिसकी वजह से ये लेफ़्ट टर्न कर होगा। और अगर मैं लेफ़्ट वाला भी ऑन कर देता हूँ और साथ C2 भी ऑन कर देता हूँ, तब भी ये मूव करेगा लेफ़्ट की तरफ, मतलब ये राइट टर्न करेगा, क्योंकि सॉरी लेफ़्ट टर्न करेगा जबकि राइट मोटर मूव कर रही होगी। लेकिन अगर C1 और C2 में ऑन करता हूँ तब ये दोनों मोटर्स मूव करेंगी, एक ऑन है और बाकी दोनों ऑफ हैं, लेफ़्ट और राइट। तो अब ये दोनों मोटर्स रोटेट करें जिसका मतलब है ये स्ट्रेट मूव करें। ये हमारा लाइन फॉलोइंग रोबोट है।
so this was just me explaining a bit of working of our line follower robot, and this one is the final look of the breadboard being placed on the top of our robot base, which had 2 wheels, uh, each of them connected to a different motor. One right one is connected to the right motor and left one is connected to the left motor. So we try to run it on the track, on the black line track, and it worked correctly. Now as we could see that it was working correctly, we could move on to our next step, which is a PCB based implementation, so that we could have a more prominent looking robot. So we use the same rudimental logic that we used earlier for multiplex based circuit, and but this time we modified a few things, like using some jumpers so that we could use them in our PCB and it could really help them in designing our PCB. So we place some of these jumpers right here, as you can see, right here and here, and then this is our PCB layout. So the jumpers that we placed earlier, you can see all of them right here, here, and here, and here too. So this is our PCB layout. Then we printed the PCB layout on a sticker paper, and then used iron to paste it on the PCB board. So after pasting it, it looked something like this, and this is before etching. Then we use the ferrous chlorides chemical to etch it and remove the excessive material. So after etching, it looks something like this. So this is our made well made Proteus PCB circuit, PCB board, but it still has some extra things to do, like drilling and component placement and soldering, etc. So then we drilled some holes in it at specific points where we wanted to place the components and for the jumpers wires. So this is our group members trying to drill some holes inside of the PCB board. And this one is a more clear look of the same task. And so after drilling holes, we place the components inside of these holes and try to solder it so that we could fix these components and later on connect wires with them where necessary to make our robot work in a more prominent way. So this is a short video of soldering. So if I play it right here, so you can see here that we are using solder gun to solder different components and make different joints here using the wire, and we have different components passed here and here, and we are using solder gun to solder them properly. And while soldering, we usually face a major issue that sometimes when we wanted to lift the solder gun after the soldering being done, we might end up we might end up doing the joint to distract from its position and connect with some other joint. So for this we had to break the joint again and then remade the joint so that we could keep it isolated in its own space, so that we don't end up messing up the entire PCB board. So if you are ever doing the soldering process, make sure to keep track of the solder gun or the joints, that they are isolated from the other joints. And so after placing the components, this is how the components looked. So we have our NOT gate here, right here. This is our NOT gate IC, and these two are our 8x1 boxes. So this is our Proteus this is our PCB circuit almost complete, and we have our remaining connections right here. And for placing these ICs here, we used IC bases so that if we ever need to if one of them ever gets some kind of faulty or some fault occurs in any of them or some leg breaks, we can simply remove them and place the new ICs there instead of doing the soldering process all over again. So Then we soldered our motors so that they can also make a perfect connection or permanent connection with the wires, instead of just hooking up the wires inside of the their pins, so that if the boat moves a little bit, or if it is at a certain angle, these wires don't just pop out, instead they stay there and make our robot a better stable version of itself. So this is our robot base bottom, and you can see here that there are wires that have been soldered here, and for placing the components we used a Vero board here, and we were going to place the components sensors downside, so that they can better focus on the wire, instead of just placing them upside down or in the forward direction, and then turn the lights toward, then turning the receiver and transmitter towards the down direction. But instead we went for the upside down approach, and place them place the center ones in the opposite directions of each other, and the two on the right and left sensors. You will understand them properly if I show you the next picture. So not this one, and this one right here, and you can see here that the sensors have been placed upside down on the Vero board, and this one is for the right and this one is for left, and the center ones are placed exactly in the same direction, just behind one another. So this one is in the front, and the previous one is in the opposite direction, pointing towards the back. So if I just point a simple direction, so this first one is in this direction, and the second one is right behind it in the exact opposite direction. So that's how this works, so that if the we did this because the line was too thin, and if we went for the side-by-side approach, then it usually end up being distracted from its path, and instead moving in a complete 360 degrees, or just stopping entirely. So let's move on to our video. So this one is a working video of our circuit, and we can, if I run it, you can see here that it is working fine. Our robot worked fine with our PCB implementation, and it is turning correctly and making stops at T. So like here it is facing three sides input. So this is the end of the video. So that's all from this video, and I hope you learned something valuable from this video, and till next time, Allah Hafiz. Thank you for watching this video.